The first problem asks you to convert 8.6 times 10 to the 13 hertz into nanometers. And in the second problem, we're going to be doing the opposite and converting nanometers into hertz. Let's first look at what we're given. We're given hertz, which is a frequency, and we're asked to look for nanometers, which is a wavelength. We can relate frequency and wavelength by using the speed of light equation. Speed of light is equal to lambda, stands for wavelength, times ni, which is the frequency. So lambda and ni. We can rearrange this to solve for wavelength, which is going to be represented in nanometers. We know that wavelength is equal to the speed of light divided by frequency. The speed of light is a constant value. We can look that up on the manila sheet, or you can just look it up in your textbook. That's 3.0 times 10 to the 8 meters per second, and you divide that by a frequency. Something to keep in mind. Hertz is equal to so many cycles per second. So we think of that as 1 over a second. In this case, if we have 8.6 times 10 to the 13 hertz, we would also have 8.6 times 10 to the 13 cycles per second. So we bring our frequency over. We look at our cycles per second. We're going to see that our seconds will cancel, and we're going to be left with the value in meters. The value that we get is going to be 3.49 times 10 to the negative 6 meters. We would want to represent this in nanometers, remember? And we also want to have two significant figures, so we're going to have 3.5 times 10 to the negative 6 meters. Two sig figs because our given value has two significant figures. And to convert that into nanometers, we use the equivalent that 1 times 10 to the negative 9 meters would be equal to 1 nanometer. And our answer to two significant figures would be 3,500 nanometers. If we were to reverse that and go from nanometers to hertz, we essentially solve for frequency using the exact same equation. It's almost going in the reverse order. We know that we have the speed of light, 3 times 10 to the 8 meters per second. The accuracy associated with the speed of light is not trivial because it's not going to define the significant figures in our final answer. We're going to have three significant figures in our final answer. So you could put 3, 3.00, 3.000. It's not going to change the level of certainty. Divide that by our wavelength. Well, the speed of light has a value in meters. So we need to represent our wavelength in meters. So again, we're going to convert the 566 nanometers to meters, and you're going to find that to be equal to 5.66 times 10 to the negative 7 meters. That number will go in our denominator. And we'll get our frequency. Meters will cancel. We're left with a value over a second. And we'll get the frequency, which is going to be equal to 5.30 times 10 to the 14th cycles per second, or